Welcome to another video. We're going to be talking about the properties of the conjugate distribution function. Alright, so there are three of them we'll be talking about, although we shall prove only one, because the rest of them could be proved by analogy. Now, the first property. The limit as some point xi approaches infinity, meaning infinity in each entry, where I is smaller than 1 is smaller than I is smaller than n, of the distribution function at some random variable x of x1 through xn is equal to 1. 2, again, we shall only prove the first one. The rest, it would be too repetitive to do all three of them. They're really just the same proof. Second, the limit as xi approaches infinity of the distribution function at x of x1 all the way to xn is equal to 0 for all j in the set of all the natural numbers from 1 to n, and for all x1 through xj minus 1, xj plus 1, so we skip xj, up to xn, which are real numbers. So essentially, an n-dimensional vector whose jth entry had been deleted or stolen. Now, and number 3, fx is right continuous with respect to all entries. Alright, so proof. It's not difficult. Firstly, we realize that xi is Firstly, we realize that what this notation means is actually means that the vector x, which is there, which has the entries x1 to xn, is approaching infinity with respect to all entries, right? So we could be just looking at it at like an n-dimensional point approaching infinity, and thus, so if we consider, xi approaching infinity with respect to all i's ranging through 1 to n, this holds if and only if the minimum for the same i's of xi approaches infinity. If it approaches infinity with respect to all entries, it must approach infinity. The smallest one must also approach infinity. This is the same thing, clearly, by our previous experience with analysis. By the monotonicity of the probability measure, we have that 1 is smaller or equal to the distribution function of x, or what the distribution function with respect to the x random variable of x1 to xn is greater or equal to fx of the minimum, as I have written above. Alright, so far nothing much clever. Now, this is sort of an interesting thing, because this is the vector which is once in all entries, and this is a scalar. That's the minimum from up here. And we want to show that we wish to show that f(x) of x times our unit vector, or whatever you wish to call it, the vector of all ones, approaches infinity for x approaching infinity. Pardon me, approaches 1 as x approaches infinity. Essentially, we have replaced the inside of the function originally up here with this, and move the limit out, which we can because f(x) is a continuous function. Denote h of x to be a distribution function of the x variable of x times all ones vector. Now, by the monotonicity and continuity, or normedness or normativity of measure, although ultimately it follows from the monotonicity of the distribution function itself. Alright, well, yeah. It holds that 1h is non-decreasing. Again, this could be obtained simply by the fact that it is defined as a distribution function, which itself is non-decreasing. And 2, that h of x is smaller or equal to 1 for all x. In other words, it is bounded, and thus the limit must exist. Hence, it is bounded, and thus the limit must exist. Now, we shall denote bk to be the set ranging through from negative infinity to k times our all ones vector. Right. Clearly, bk converges in the mean to the n-dimensional real space. Clearly. Thus, by the continuity of px, we have that the limit as where k is a natural number and k approaches infinity of h of x, or h of k, which is equal to the limit as k, where k is a natural number and k approaches infinity, of f(x), well, x is our random variable, of k times all ones vector. Now this is equal to the limit as k approaches infinity of px of bk, well, of course bk is equal to our set from up there. Now this holds by the definition of the distribution function, and of course since px is a continuous function, we have then that it is equal to the px of the limit as k approaches infinity of bk, which in turn is equal to px of the whole real space and dimensional, which by the definition of px we have is equal to 1, which is precisely what we wanted. Points 2 and 3 could be proved by analogy, and this concludes the proof.